So we've spent several videos now talking about electrophilic aromatic substitution, but there's also a thing called nucleophilic aromatic substitution. In electrophilic aromatic substitution, benzene's pi electrons attack an electrophile. In nucleophilic aromatic substitution, benzene is being attacked. Benzene is the electrophile. But aryl halides, benzene stuff, is typically unreactive towards substitution, meaning if we try to do some sort of SN2 reaction where our nucleophile attacks and that Br gets kicked out, not so much, because a nucleophile is repelled by the pi electron cloud. Remember, these pi bonds, there's a cyclic donut, a cyclic pi cloud above and below the plane of the molecule. That pi cloud blocks the incoming nucleophile from attacking like this to do an SN2. And if you were to do an SN1, that means that bromide is going to leave and leave behind an aryl carbocation. No. Aryl carbocations, So aryl halides are typically unreactive towards substitution. If you add Naomi and Home to this aryl halide, you don't get the product. It's typically unreactive towards substitution, unless you heat it really, really, really hot. If you heat it really, really, really hot, you can get substitution to take place. This nucleophile, this is the nuke. Naomi, remember, is ionic. Naomi and Home can attack this electrophile. How does that mechanism work? Let's see. Naomi is the nucleophile. Naomi attacks the carbon that has the electrophile, the carbon that has the leaving group. So we said you cannot do SN2. So Naomi does not attack and bust out that chloride. Not happening, not a thing. Naomi attacks, and we end up creating a lone pair over on the corner like that. That pi bond moves out of the way. Scoot over, man. I need room here. Like that. And then that complex, like all these others, has a name. That's called a Mesenheimer complex. Every time I hear that, I think of Jingleheimer, John Jacob Jingleheimer Schmidt. His name is my name too. I know, it's silly. Mesenheimers all have resonance, just like Weyland's do. So this Mesenheimer complex can be drawn this way. Oh, that's a CO. Whoopsies. Resonate on around. Lone pair moves. Creates a new lone pair. New lone pair. That was a lone pair there. You don't have to show me those dots, but sure. This Mesenheimer has 3 resonance structures. Those 3. And finally, that lone pair can fold in and kick out my leaving group. So this is not SN2. This is not SN1. SN1 goes through a carbocation. We definitely do not make that. SN2 is concerted. We definitely did not do a concerted reaction. We had a 2-stepper here. We did an addition reaction, or not an addition reaction, but an addition step, where the Naomi added to my benzene. Naomi added, that's my addition step. And then I did an elimination step where my lone pair folded in and kicked out my leaving group. Elimination is the second step. Addition happens first, then elimination. We get this. This mechanism, oddly enough, is not SN1. It's not SN2. It's SNAR. I know, that's crazy. We have such crazy names. That stands for substitution nucleophilic of an aromatic thing. Substitution nucleophilic aromatic. Aromatic rings cannot do SN1. Aromatic rings cannot do SN2. If they're going to do substitution, it has to be through a SNAR mechanism like this, or one other kind. So we said these things generally need to be heated to a really high temperature. This one we said works at 350 degrees. But this one works at 160. Wonder why that's the case. Let us see. Hydroxide is the nucleophile. Hydroxide attacks the carbon that has my leaving group on it. and I make a John Jacob Mesenheimer Schmidt, an OH up here, like so. All Mesenheimers have resonance. So if I start drawing my resonances, lone pair folds down, makes me a new lone pair down there. Lone pair folds on around, makes me a new lone pair over there. And then an N and an O and an O and a minus and a plus. Every Mesenheimer has resonance. Every Mesenheimer has at least 3 resonances. But some Mesenheimers have more than 3 resonances. This one has more than 3 resonances. The 4th resonance picture is if that minus did not go on around the benzene, that minus, that lone pair, could have been shared to make a double bond between the nitrogen and the carbon of my benzene. It's not benzene anymore, but you know what I mean. The carbon of my ring thing. And that leaves me with 2 O minuses and an N plus, like that. If I analyze the blue structures versus the purple structure, the purple structure is actually better than the blue structures because the purple structure has oxygens with negatives instead of carbon. All of my resonances have a full octet. That's very different about a Mesenheimer versus a Weyland. All of my resonance structures have a full octet. So it's formal charges and formal charge negative on oxygen and carbon in all the blue ones, negative on 2 oxygens in the purple one. So the purple one is actually the best. Winner, winner, chicken dinner contributes most to the hybrid. In any of these mechanisms, electrophilic aromatic substitution included, I have generally taken, in electrophilic aromatic substitution, I've generally said some base and taken the hydrogen off of my last resonance structure of the Weyland. It doesn't matter which one you take it from. Same thing here. You can decide to use any of the resonance structures to kick out your leaving group. It just depends on, the only thing that's different is how many arrows it will take in order to get your leaving group gone. That's what I'm trying to say. I could have chosen this structure, and it would be 2 arrows to get my leaving group to go. If I choose the purple, it takes 4 arrows to get my leaving group to go. It doesn't matter which one I choose to remove it from. You can do it from the very first structure. Whatever. It doesn't matter. Okay. So then I end up with my green final product, nucleophilic aromatic substitution. Nucleophile adds to the benzene to the carbon that has the leaving group, makes a Mesenheimer intermediate. Lone pair folds down and kicks out my leaving group to where that nucleophile has been substituted for the halogen. We're going to see nucleophilic aromatic substitution with aryl halides, with halogens on benzene only. So I pointed out when we first flipped to this page that this one happens at 160 and that last one was at 350. Why do you suppose that's the case? This Mesenheimer is more stable than this past Mesenheimer. Why? Because this Mesenheimer has 4 resonance contributors, while that Mesenheimer has 3 resonance contributors. More resonance contributors means more stable. More stable will mean a lower activation energy to get there. Lower activation energy, lower temperature as well. So what is my interpretation of that? Well, this, I know, is an electron withdrawing group, and that electron withdrawing group actually served to give me this extra resonance picture. So electron withdrawing groups are great for Mesenheimer intermediates. Great, excellent, fantastic for Mesenheimer intermediates. They're bad and deactivating for Weyland intermediates, but they're extra stabilizing for Mesenheimer intermediates. Yeah? Electrophilic and nucleophilic, they're different. So if that last one happened at 160, why do you suppose this one happens at 100? Because it's got not 1, but 2 electron withdrawing groups. If we don't draw the whole mechanism here, we can draw part of the mechanism or we can draw the mechanism without all the resonance. That's what I really mean. NO2, lone pair, minus minus, that's a pi pi. And I can fold down and kick out and make my product. Well, it's just a phenol, either way. But the big picture is it happens at lower temperature. Why does it happen at a lower temperature? Because you have two electron withdrawing groups. What good do those things do for your Mesenheimer intermediate? You'll get there eventually. Mesenheimer intermediate. It helps stabilize by creating two extra resonance pictures. So every Mesenheimer has at least 3, but this Mesenheimer will actually have 5 intermediates. Could you imagine what might happen if we put a third nitro group on there? It happens at nearly room temperature. And the truth is, it probably could happen at room temperature. I kind of think your textbook puts it at room temperature. It happens real close to room temperature, regardless. You make this thing, that picric acid that I mentioned before. Yeah, go boom. All those deactivating groups, all these deactivating groups are bad for electrophilic aromatic substitution. They are bad for Weyland intermediates. They are fantastical for Mesenheimer intermediates. Weyland and Mesenheimer are complementary pairs. What's good for one is bad for another, and vice versa. This mechanism only takes place in the presence of strong electron withdrawing groups. And it should be heated. My cat's going a little crazy tonight. If you see a halogen on a benzene and something with a nucleophile, lots of nucleophiles can be used, a halogen on a benzene and a nucleophile over the arrow, especially if that nucleophile is heated, think nucleophilic aromatic substitution, think Mesenheimer intermediate. We can have all of the halogens be leaving groups, but actually fluoride is the fastest leaving group, and iodide is the slowest. There's a little bit of information in your textbook about why, but we're not going to actually go through why. But lots of things can be nucleophiles. Could you heat this thing and cook it and cook it and cook it and cook it? And could you get it to form this thing? No way. This, first of all, is a terrible, horrible, no good, very bad leaving group. If we look at it another way, as in hydroxide will have to be a product over here, and you can think of chloride being a reactant over there instead of a reagent over the arrow. Acids and bases, they always favor the weaker acid side, the weaker base side. This base is so much weaker than that base. So elimination, so equilibrium would favor the reactants side. So it doesn't matter if you try to turn other types of benzene into displacing, if you try to displace other groups on benzene with a nucleophile, it's not generally going to work. The halogens are fantastic leaving groups because they're such weak bases. So this guy, you can't do that. Okay. Again, lots of nucleophiles can be used. So what about this one? Well, long years ago, when a chemist was doing this reaction, they observed that that product was made, as expected. But they, Mr. Roberts, noticed that it happened at negative 30 degrees Celsius. We just said you need to heat, back here, we just said you need to heat these reactions because you're making a complex that's pretty high energy most of the time. You need to heat those things in order to get it to work. But Mr. Rogers got this, Mr. Roberts got this to work without heating. It worked at negative 30. Note, this NH3 is liquid ammonia. Liquid ammonia has a boiling point of negative 33, so they were lower than the boiling point so that they could be ran in NH3 as a solvent. So he ran another experiment after this, and he found that if you do this same thing to this, you get no reaction. So he said, I'm not sure this is going through a Mesenheimer intermediate. I'm not sure that's what's happening here. He proposed a different type of mechanism, a different reaction. It's this one. He said, what if I do a traditional elimination? This is a strong base, NH2-, strong base. So let's do some E2 elimination. It's a little bit different because it's on a benzene kind of ring, but let's do some E2 kind of elimination. And let's make that intermediate. What? Yeah, it's a benzyne. It's an alkyne within a benzene. Oh, man. Benzyne is an extremely reactive species. Yeah, it's an extremely reactive species. A normal alkyne has good overlap between these things to give you a good pi bond. But trying to get a 180-degree bond angle, which is what an sp carbon usually is, between two carbons in a six-member ring, not so much. So benzyne has been proven to exist, and I'm going to explain how. It has been proven to exist, but it's an extremely reactive species. So it doesn't hang around for a super long time to do a lot of other things with it. So instead, what can happen is one of your NH2 molecules can attack that carbon, like so, where your chloride just left, and you get this out of it, with a little negative over there. This is not a Mesenheimer intermediate. If you look back, it's too many clicks backwards for me to go all the way back. If you look back, a Mesenheimer, for one, had two things on a carbon at once, and it had a negative charge, but it was not a benzene with a negative charge. This is still 3 pi bonds with a negative charge over there. That's an aryl anion, different from a Mesenheimer. So that aryl anion can then take a hydrogen from your solvent, like this, and give us aniline. I'm drawing that hydrogen for no real reason. I just did. So you might say, that's all well and good. Why did that man propose this mechanism? What's wrong with making this do a Mesenheimer? Again, Mesenheimers must be heated, and Mesenheimers work best when your ring is deactivated. If it's not deactivated, that Mesenheimer has to be pushed to extreme temperatures, very high temperatures, in order to react. This one happened at -30, quickly, easily, and he got aniline out of it. So I said I was going to prove to you how we know that this benzyne is a legit intermediate in this reaction. What Mr. Roberts did back in the day, a long time ago, was he did a very sophisticated reaction where he specifically labeled the carbon that has the halogen on it with an isotope of carbon, a radioactive isotope of carbon. Carbon-12 is 98.5% of the carbon on the planet. Carbon-13 naturally exists on the planet as well. Carbon-14 is radioactive carbon. So he labeled this carbon with radioactive carbon-14. And he observed that in the end, he got some product where that carbon that has the nitrogen on it is the radioactive carbon. And he got some product where the radioactive carbon was ortho to where that amine is. And when that radioactive carbon was ortho, he said, that's interesting. Maybe I will propose this benzyne intermediate. And he did several more experiments, and we're going to talk a little bit more about them in a moment maybe. But how does the nitrogen get to the other side? How does this green product get made? That's if the nitrogen, the NH2-, attacks the other end of your alkyne. So what he really sort of said in the beginning was, if I get it in both places, it must mean I go through some sort of symmetric intermediate. And that symmetric intermediate that he came up with was this benzyne stuff. And that has undergone several other experiments to prove that benzyne has to be what's happening, even though it looks super bizarre. So in this particular example, we don't get different products unless there's like a radioactive label on one of the carbons. We get aniline, it's purple. We get aniline, it's green. It's still aniline. but sometimes you get different products. I was ready to move on, but then I remembered I did not point out this is called an elimination addition mechanism, because the first step was eliminate a beta hydrogen and then add your nucleophile. Mesenheimer is the opposite. Addition, elimination, benzene, elimination, addition. Both of those mechanisms are nucleophilic aromatic substitutions. Both of those mechanisms require that you have a leaving group, and you're going to end up with some sort of nucleophile taking the place of that leaving group. Yeah? Okay. Now we're really, really ready to move on to the next example. Some of them create multiple products. Like this one. Here's my alpha, my beta. Oh, look, I've only got one type of beta hydrogen. Something I didn't point out in my last example was that it was a symmetric thing. There were two types of beta hydrogens in that last one, or two beta hydrogens, period, but only one type of beta hydrogen. I should have drawn it consistently the way that it was over there to not add confusion. I apologize. Okay, so we get this benzene and NH2 minus can attack this side, which did not have the halogen, to lead to this intermediate and this product. But we also could have had our NH2 attack this carbon, leading to this intermediate, and after protonation with the solvent, this product. This is interesting. We made a mixture of ortho substituted stuff and meta substituted stuff. In electrophilic aromatic substitution, you don't ever get an ortho and meta mixture like this. You're only going to get an ortho-meta mixture if you went through a benzene intermediate. Weird. So another way that Mr. Roberts, continued to prove that his benzene intermediate was feasible was doing reactions like this and getting this ortho-meta mixture and saying, guys, this benzene is the only thing that makes sense, even though it looks so weird. Yeah. NH2 is one of the most common nucleophiles in order to do a benzene reaction, but it's not the only nucleophile. I should have said this prior to now, but I just wasn't thinking clearly because it's late and I'm tired. What's mandatory is that you have a strong base in order to deprotonate that beta hydrogen and make this benzene. It's got to be, in my words, a super strong base. I know, that's crazy. Where's the line of super? I would call hydroxide and everything to the left on our acid-base chart of fun, I would call hydroxide and everything to the left a strong base. I would call NH2 minus and everything to the left of that a super strong base. That really means alkanes with a minus, alkenes with a minus, and amines with a minus. Those are the ones we qualify as super strong bases. Hydride is actually probably too weak of a base to make a benzene. So we could have an alkane with a minus, like this organolithium, super strong base. There's only one type of beta hydrogen. There are two actual beta hydrogens, but only one type. I'm going to choose to take this one because that's where my other pi bond already is, but something that confuses students a bit sometimes. If my pi bond were over there, I would choose to take that hydrogen, but this is benzene, and you must always keep in mind that benzene has resonance of those pi bonds, so it doesn't really matter which beta you take. You just take the one that's on the side, at least if it's a symmetric one. You take the one that's on the side that already has the pi bond in place so that when you add a new one, it makes an alkyne. Maybe that makes sense. I'm not sure. I said it weirdly, but you've gotten used to that by now. Okay, so then your base can attack the position that had your leaving group or the one next door, but you're going to end up with the same product in this one. And we get this aryl thing. And CH3Li methyl lithium is such a strong base that that's just going to hang out as this aryl anion. So crazy. That's just going to hang out as an aryl anion until you add something to quench your reaction, to stop your reaction from happening, to put an end to your reaction. And we've added water. It's got to be something that's acidic, but very mildly acidic, as in water is acidic enough to neutralize my aryl anion for sure. For sure. So I get this. It's toluene. Why would anybody go to the trouble of making chlorobenzene and then turning chlorobenzene into toluene? A lot of people would not. You could just alkylate benzene directly with Friedel-Crafts alkylation. But sometimes when you have other functional groups around here, something like this might be your only option. But electrophilic aromatic substitution, for one, we talked about it way longer, so y'all are probably much more comfortable with it. But sometimes it doesn't work in all situations, electrophilic aromatic substitution, that is. And nucleophilic doesn't work in all such situations either. So this is just another way to make toluene. All right. What about this one? This one is symmetric, which means I only have to worry about making one type of benzyne, and that's this benzyne. And without the rest of the mechanism, because maybe we've drawn it enough and you can rewatch this video anyway, we get this product and we get this product. In benzyne mechanisms, we're not going to talk about which one's the major and the minor. Oh, shoot, that's the same product. What you doing? In benzyne mechanisms, we're not going to talk about major and minor most of the time. This is a completely symmetric intermediate. So I would really expect a 1-to-1 ratio, a 50-50 mixture of these two things. I would not say one is a major, one is a minor. But sometimes you might have a major and a minor. This is not a symmetric benzene. I can take this beta hydrogen. Oh, that's beta. Oh, man, I should probably stop recording because I'm really just saying everything wrong. You can take this beta hydrogen and make this benzyne. Green benzyne, we'll call it. You can take this beta hydrogen. We're going to need to look at the resonance in order to take that beta hydrogen. Consider the resonance. NH2 can take this one and make this benzyne. And if NH2 attacks here, I get NH2 here. And if NH2 attacks there, I get NH2 there. No, that's crowded. Maybe one day I'll draw smaller. Nah, who am I kidding? We got a meta and a para from this purple benzyne. From the green benzyne, we can get a meta if it attacks here. And we can get an ortho. X. That's two H's over there. We can get an ortho if it attacks directly adjacent to the methyl. In this reaction, we observe ortho and meta and para. We get all three of those as products for this reaction. For this one, I would actually expect that meta is the major. Any ideas why meta might be the major? Obviously, there are two pathways that made the meta product, so meta is the major simply by numbers for statistical purposes. There were two ways to make this. It's twice as likely to happen versus there's one way to make para and one way to make ortho. So, yeah, it's just numbers game. Benzyne mechanism. You gotta know it. In this one, I don't have any beta hydrogens. So this one cannot do a benzene. But I do see that I have a halogen. So can I do a nucleophilic aromatic substitution addition-elimination mechanism, meaning make a Mesenheimer intermediate? No. Why can I not make a Mesenheimer intermediate? Because a Mesenheimer must happen on a deactivated ring. Or, in the slight chance that it's not deactivated, it could possibly happen on a simple aryl halide. But we have not one, but two electron donating groups. And when you have EDGs, Mesenheimer is not possible. So benzene is not possible because I have no beta hydrogen to eliminate. Mesenheimer is not possible because I have donating groups. Additionally, this doesn't really exist above -30, so I couldn't even heat it and hope that a Mesenheimer would work. It ain't happening. So nucleophilic aromatic substitution. Nucleophilic, we talk about way less than electrophilic aromatic substitution. So students generally get to the point that they feel pretty comfortable with electrophilic aromatic substitution, but they feel a lot less comfortable with nucleophilic aromatic substitution. We don't spend nearly as much time on it because we've spent so long on other types of substitution, as in SN1, SN2, E1, E2 kind of stuff. Those SN1, SN2 days, we talked about nucleophile after nucleophile after nucleophile. Tons of nucleophiles can be used to make a Mesenheimer intermediate, so we don't go over quite as many examples of all that because it's just nucleophile after nucleophile after nucleophile doing the same dang thing. So how do I know if I should do a benzene intermediate or a Mesenheimer intermediate when I'm presented with a problem? That's a question that many students struggle with for a long time when they learn about this. Number one, to do nucleophilic aromatic substitution, period, you must have a leaving group. And we said the halogens were our leaving groups. Okay, so if I see a benzene that has a halogen on it, I may not do nucleophilic aromatic substitution, but I've got it on my mind that's something that's possible. Then if I look at my reagent arrow, the reagent arrow must have a nucleophile. If that reagent arrow has something like sulfuric acid, that's an electrophile. If it has something like nitric acid and sulfuric acid, that's an electrophile. Those are electrophiles. If it's something like Br2 and FeBr3, that's a Lewis acid catalyst, that's an electrophile. Something like AlCl3, that's an electrophile. So if you look at the arrow and it has one of our big five familiar reagents, that's going to do electrophilic aromatic substitution. But if that arrow has nucleophile over it, you will potentially do nucleophilic aromatic substitution. So first of all, if you have other reactive groups around, meaning if you have something like this and you add a sulfur compound, that's a primary benzylic substrate. Reacting on the side chain is much quicker, much more efficient than reacting on the benzene. That's not a aryl bromide anyway, so we're not going to do nucleophilic because the bromide is not directly connected to the benzene. But beware of side chain reactions being different from direct reactions on the benzene. That's another word of caution. So you must have a nucleophile. That's often ionic things like O with a minus, S with a minus, carbon with a minus, nitrogen with a minus. Yeah. If that nucleophile is heated, check to see if your benzene is deactivated. If it's heated, check to see if the benzene is deactivated, and if it is deactivated, we're thinking Mesenheimer. John Jacob. If it's not heated and a super strong base, think benzene. Are there tweaks and things that could be made all along the way? Sure. But, number one, nucleophilic aromatic substitution must have a leaving group, and we've seen halogens be leaving groups. The arrow must have a nucleophile on it. That nucleophile, if it's kind of a mild, gentle nucleophile, even if it's a negative thing like sulfur minus, oxygen minus, probably going to go through Mesenheimer, but probably should be happening on a deactivated benzene, and you need to cook that thing for a while. If it's a super strong base, or not deactivated, yeah, I said that. I should say, nah, I don't want to say and, I don't want to say or. If your benzene is activated and your base is super strong, let's do benzyne. If your benzene is deactivated, let's probably try Mesenheimer. That might be the worst summary ever of nucleophilic aromatic substitution, but it's all I got at this late hour. I apologize. All right, that's a wrap.